All right, everybody, welcome. Welcome to the online workshop. My name is Drew Jones. I am the Executive Director of Climate Interactive. I'm here with Ava De Leon and Jen Turliuk, and we're so excited that you're here for AI and Climate. AI and Climate with En-ROADS. That's what we're going to be digging into. In the meantime, please let us know where you are in the world. Go and open the link you probably see in chat, or you can see it at the top here. It's a pollev.com link. We're going to be using Poll Everywhere to get some of your thoughts about this issue. Go drop a pin somewhere on this map. We're curious where you are in the world. Or write in chat. Write your name, your location. If you happen to be an En-ROADS climate ambassador, put that in the chat as well. Introduce yourself to everybody. Everybody, these are the 784 people around the world who are trained in using En-ROADS to engage others in finding equitable climate solutions. We got people in the East Coast of the US, the West of the US, up in Canada, the UK. I see Pakistan. I think that's Nepal, South Asia. So we have folks around the world. Welcome to the webinar. Thrilled that you're here. Open the poll. Let us know where you are. Go into chat. Let us know where you are. It's amazing. There's a community of people around the world using interactive simulations to enact effective, equitable policy. And as Jen Turliuk said a minute ago, as we were getting ready for this, being wise about our use of cool new technologies like AI. Can we be wise about our use of these technologies to create equitable and stable climate futures? A lot of people writing in, thrilled to see you all here. Jen, your thesis advisor, John Sturman is here. Welcome, John, from Cambridge, Mass. You did a lot of the foundational work that we're going to be talking about today. Great to see you. And a lot of familiar names from the world of En-ROADS climate ambassadors. If you're just joining, my name is Drew Jones. I am the co-founder, executive director of Climate Interactive. I'm here with Ava De Leon and Jen Turliuk. We're going to be looking at AI and climate. You're letting us know where you are, but actually not anymore, because we're moving on to the second question. We're so curious to find out what's been your experience with En-ROADS? If you know what I'm talking about, answer A, because you're learning about it for the first time. Maybe you've just seen it presented in a workshop at MIT or by our partners at Climate Pathways Project or by somebody around the world in the 21 languages. Maybe you've played with it yourself. That's the next level. Maybe you actually got to show it to others as a facilitator in a game or just a demo, an informal demo. Or maybe you are a proper trained En-ROADS climate ambassador. Actually, Ava, would you post the link to the website that has all of the ambassadors so people can see all those people who are out there around the world? It is a pretty even mix of all of you, helpful to see. Great. All right, let's get going with the event itself. And okay, we are a not-for-profit climate tech company, Climate Interactive, and we see two big problems in the world. The analysis that's getting to top decision makers is not adequately grounded in the best available science. Too much propaganda, too much marketing, too many just intuitions guiding the policy around the world. Can we get best available science in the hands of top decision makers? And the second problem is when it gets to top decision makers, often it's just research. It's just a paper. It's a PDF. People don't change their minds. John, you're here on the call. You said it best. This is John Sturman at the System Dynamics Group at MIT. He said, research shows that showing people research doesn't work. Therefore, we embed the research in the simulation model that allows people to think for themselves. That's what we're going to do today. We're going to help you think for yourself about the impact of AI on climate using an interactive simulation. John's part of the team at MIT, the Sloan School of Management, and the MIT Climate Pathways Project. Our guest star, if you turn on your camera, is Jen Turliuk, who just turned in her thesis and is getting her MBA out of the Sloan Fellows Program. Welcome. And Jen's going to share some of her research. Anything more on you and your background, Jen?
Sure. Yeah, I'm practice leader of climate and energy AI at MIT's Entrepreneurship Center. So I build, research, and instruct AI for climate and energy solutions, and also just wrapping up the mid-career MIT Sloan Fellows MBA program. So super excited to be here. I've really enjoyed watching the webinars, and I'm really excited to be on this one.
Great. All right. And Jen built a cool chat bot for En-ROADS that we're going to hopefully get out there to the world at some point. We should post that. Isn't there a version you want to post? Ava, please go ahead and post that if there is a version that we're able to play with. All right, full transparency. Here are the visionary funders that make this work possible. And as you know, our theory of change is to get this tool to you and others around the world. All right, the headlines that motivate this. New York Times headline, and so much. The Pope this morning talking about AI. It's the flavor of the month. AI's insatiable appetite for energy is often how this challenge is framed when it comes to AI and climate. So we have bad news and good news on what you're going to hear in this webinar. The bad news is we don't have definitive calculations about AI's impact on the climate, either for better or for worse. The state of the science and the understanding and the modeling is just not there. You're not going to come out of this saying, oh, Climate Interactive at MIT think the answer is X. Not going to happen. That said, we've made some advancements in thinking about it and using an integrated assessment model, En-ROADS, to test it. And maybe I should just say a word about En-ROADS. That is this tool. And Ava, can you post a link to the simulation itself? We're going to be thinking about AI and how it is going to affect the climate, emissions of CO2 you see here, temperature over on the right, by changing some of the policies at the bottom of the screen here. And I'm going to click, for example, if we had transport energy efficiency, you can see it changes things. And for those new to En-ROADS, it is running the full model every time we move a slider in this integrated assessment model. And it can do so in the 21 languages. Go play with it. This is the context of how we're going to be testing some of these scenarios. But the framework that we offer is not just the energy question, although it's important, and Jen's going to share some of her analysis on it. The energy demand, that is energy use from AI in data centers. That's one of 4 areas. And for you users of En-ROADS and you facilitators, it's happened to me several times. People raise their hand and they say, what will be the effect of AI on climate? We encourage you to answer with as many of these 4 areas as possible. This is the framework I want to offer you all. 1, energy demand. It takes energy just to run AI. 2, solutions. This is the possibility. Maybe we will get strengthened mitigation, avoidance of emissions in energy, land, forest, industry, and on. Third, already over the last decade or so, people have been using AI to increase oil and gas production, discovery, yields, lowered production costs. How much will that affect this overall system? That's the third big impact. And the fourth is the economic rebound effect. That is, this is a tool to boost productivity. If you boost productivity, GDP per capita goes up. Overall GDP consumption goes up. Energy demand, more energy demand means more burning gas and coal via electricity. and that will lead to more emissions. This is a rebound effect over the entire economy. Note, there's another rebound effect that we will explore just within the area of the AI technology. But main takeaway you're going to get, I'll show this at the end, is this four-part framework. And in answer to the question, what's the effect of AI on climate in a manageable bundle? We think you should say, try to answer these four questions. And that's what we're going to do together. I want to hear, though, your mental model about your answer to this question. We're very curious about what we call mental models. That is your understanding of the system and really your mental simulation of it. So go to the poll. What do you think the net effect of A on greenhouse gas emissions relative to the baseline by 2035, next 10 years, is most likely to be? A big increase over 20%, a smaller increase? Why does it say 15? I fixed that. Darn it. That should say 5 to 19. Neutral, a small decrease, or a large decrease. So most of you are coming into a small increase. Nobody thinks there's a net benefit. Wow. Now there's a lot of selection bias of who shows up to our webinars. Okay, there's somebody with some courage that they believe that. E. Okay. So most of you were hearing small increase. That's your mental simulation. 98% of decisions that are made with models. Well, all decisions are made with models. Most all of them, the one between our ears. Right now, we want you to simulate your mental model and tell us what you think with your current understanding. Okay, most think a small increase. Second question, I just laid out 4 areas. Which area is where you think there will be the biggest net impact? When I say net impact, it could be increase, it could be decrease. Increased energy use for AI and data centers is what's getting the most votes. Increased oil and gas production, which would increase emissions, or increased via GDP growth via this rebound effect I described. B would be the potential to reduce emissions through strengthened climate solutions. All right, well, it's most votes for energy. Helpful to see. Okay, I'm glad then that we chose that as the first one. So that's the first one of the 4. So energy use. And Jen, you in your thesis, which looks like this on a cover page. And if you go into chat, if you want to see the thesis when it's being shared, go into chat and look at that and go ask to get a copy of it. You ran a calculation. What's your calculation?
Sure, I'm happy to share that. And also a big shout out to John Sturman, who was super helpful as an advisor. It was great to work with him. So basically what I did is I looked at, and what we did together was looked at the net climate impact of AI. So considering not just the current environmental costs, but also future potential environmental benefits, including things like the installed base of existing hardware chips, as well as the time value of carbon, and finally rebound effects. And so for on the emissions side, we looked at 4 key factors: the population, the GDP per capita, AI compute per GDP, energy per AI compute, and emissions per energy, and found that AI contributes 0.03 gigatons of emissions. That's based on looking at 2 of those key factors, which is the amount of data center power that's being used by AI, as well as the average grid intensity. And then when we looked at the net climate impact of AI, including both costs and benefits, we found a range of a 0.55 gigaton harm to 0.72 gigaton benefit.
Great. Thank you. Yeah, and let's just note, grab that number, 0.03 gigatons per year.
For
And
2024.
I'm going to share how we use En-ROADS is, let's put that into perspective. this is going to be relative to what we see as the baseline here in En-ROADS. And 0.03, not 0.3, but 3/100ths of a gigaton relative to the total right here, which is right now, 2025, about 60. So it is 0.05%, a very small increase relative to the global. So I want to use this in two ways. First, to say this first calculation is it's relatively small, and we want to use En-ROADS to think about systemic, system-wide impacts as well. There was a second set of numbers that you mentioned that we're going to come back to later when you incorporate the effect of solutions. But I want to just also complement your analysis and point all of you listeners to other analysis that fills in how much and where. International Energy Agency has this report. Please, Ava, if you would post it, energy and AI. And what they did, probably similar to your analysis and your model, was to run different scenarios. This is global data center electricity consumption for 4 different scenarios out to 2035 in terawatt hours. Now note, this is data centers. And you all found this very helpful number from Goldman Sachs, 14% of overall data center energy, electricity use for AI. Now that may change over time, but so it's a fraction of this. Now they looked at 4 different scenarios based on efficiency improvements, bottlenecks for energy supply, the growth of AI and AI use. So there's some different ranges that we could look at that should be considered, and also where. Look at figure 212, where they noticed where it is. The green area would be in the United States. Blue is China, Europe, and then other areas of the world as well here in this stacked graph. Now note, this is going to incorporate, and any calculation needs to consider the rebound effects. That is, things are going to get more efficient overall. And so there could be algorithmic, this is how Jen, you and John framed it, algorithmic and hardware efficiency improvements. In fact, you may have seen a couple of weeks ago, DeepSeek out of China was reporting 50 to 75% less than competitors. So there's some potential that overall less energy could be used. We've seen some data to say that actually those gains might have stalled out over time. But Jen, you and John did also point out the importance of a rebound effect when it comes to these efficiency improvements. And this is incorporating a systems thinking idea, the Jevons paradox, the Jevons effect, or the rebound effect. And that is that a technological advancement is going to make some resource more efficient to use. That is, AI gets more efficient over time. However, if it gets more efficient, it gets cheaper, so people use more of it. Therefore, it may consume or balance out some of the savings. So that needs to be considered as we're figuring out how much efficiency gains might help reduce the energy effect of overall AI. So we don't have a definitive number. You heard one calculation, 0.03 from Jen's thesis, but this is a big question mark right now. In fact, we just put in a proposal to a foundation to add it explicitly to En-ROADS. My dream is that in 6 months or in a year, you're going to be able to explicitly make a change in En-ROADS and see what is that calculation. How would you simulate it in En-ROADS? Let's go try it. The place where we think should go test it at this point, given the En-ROADS that we have today, will be in this area of economic growth in the context of this baseline. And I haven't shown you just where we're starting. So let me just step back, show you the baseline, and then show you what an effect of AI energy use might be. What's critical with AI energy use is to go to, say, our 12 favorite graphs. One of them is energy consumption. Overall energy consumption is driven by overall population and GDP, those two things down here. If we have fewer people or more people, that's going to drive overall energy consumption over on the top left. And economic growth, we make assumptions it could be lower, it could be higher. And then the energy intensity of that consumption. How much energy, how many exajoules per year does it take to deliver $1 billion of goods and services? That is the energy intensity. And those things come together into this overall energy consumption. One important thing to note is we're already assuming massive drops in energy intensity. We're already counting on technology and a shift from a manufacturing economy towards services to bring down how much energy it takes to deliver GDP. And this is an increase in energy efficiency and increase in energy conservation. We're already assuming a big drop in this. So later, when we test energy efficiency from AI, improvements from AI, we should consider this fact that we're already expecting a good bit of drops. All right. So what we have here is overall energy demand. We have greenhouse gas emissions. And given this pollution going into the atmosphere, coal, oil, gas, deforestation, methane, nitrous oxide, F gases, some removals is all incorporated here. That's the temperature we get. If you want to test AI, if someone says, hey, what about the energy use of AI? Go here to economic growth and quite simply move it up a little bit. This will increase consumption. This will increase the use of an energy sources to provide the energy needed for AI. So it will look something like this. Now, we don't stand by this exact slider move. I can't tell you it is exactly a change from 1.5% a year's long-term economic growth to 1.7, but this is how it'll affect the system. And this is the timing, that it is steady and slow growth over time. You could argue that it's also going to drive near-term economic growth, perhaps as well. This is a simple way to show emissions would go up. Why are they going up? Because if we had around the world, don't think of the United States, think of China, India, Indonesia, Argentina, Brazil, South Africa, Mexico, fast-growing nations. Where would we get that energy? Well, particularly in China, we'd have to have more from coal. It can't be done just with nuclear and renewables. We'd have some more natural gas as well. We would get more renewables, but a mix of many sources. If we burn more coal, if we burn more gas, then overall greenhouse gas emissions would go up a bit. That's how to test it here in En-ROADS. Okay, that's one of four. Let's move on to number two. Number two is the promise, is the possibility that maybe these technologies and AI can help us reduce emissions by boosting solutions. So Jen, tell us about what kind of possibilities you see in that area, and I'll share that slide about this. I'm going to pull it up.
Okay, great. And while you're pulling it out, I just want to also give a huge shout out to Harvey Michaels and Jason J, who I can see join the chat as well, join the call. Harvey was also an advisor on my thesis, and Jason was instrumental as well. So I want to talk about some of the solutions in terms of AI and what AI can bring. So AI can do a lot of powerful things like collecting and monitoring complex data sets, also strengthening decision making and helping to optimize processes. It can also help do things like accelerate materials discovery and innovation and improve climate and policy modeling. In terms of energy, which is one of the biggest areas we see of emissions that are driving climate change, some great work from Priya Danti and colleagues at MIT and other universities broke down the applications into energy production and consumption, energy transmission and distribution, and cross-cutting applications. And some of the applications I'm most excited about are first on the left, solar and wind prediction and electricity demand prediction. If we have better predictions of these, that can allow us to do the top part, maximize renewable power generation, so we don't necessarily end up creating as much fossil fuel driven energy at times where we don't have as good predictions. And then also on the top right, there's predictive maintenance and fault detection. So, for example, solar panels, there's huge farms of solar panels, and some of them might be broken, but it's difficult for the human eye to figure that out. Would you fly over it, walk under it? What would you do? But with large aerial images that go through machine learning, you can easily identify which solar panels are broken. And energy data management's a really key area too, as well as informing policy. There's huge amounts of policy documents, and machine learning allows us to sort through them and identify opportunities for improvement. We can go to the next slide. I just want to give an example on the load flexibility side. So imagine 10 consumers all drive their electric vehicles home to the same neighborhood and they plug in at 6 p.m. on a Monday night. This could create what's called a peak load, a spike of energy demand that the physical grid may not be able to handle. So what might we do to solve that? We might add more physical grid infrastructure, but this is both expensive and time consuming and may not allow us to meet our climate goals. What if instead AI was installed at that site so that instead of the cars all starting to be charged at 6 p.m., they were intelligently managed to charge at different times throughout the night, so everyone woke up with their cars charged. This is an example of, we can go to the next slide, peak shaving or load shifting, where we shift the load around to either reduce it or move it to different times. And this enables us to reduce the amount of emissions, increase the amount of renewables needed, and not need as much expansion of physical grid infrastructure. So that's on the load flexibility side. And we can go to the next slide here. There's also lots of opportunities to reduce the amount of greenhouse gas emissions from buildings and cities using machine learning. Again, from the similar paper and organization Climate Change AI, which has really great resources to learn more about all of these areas, we see that AI can be used in things like modeling buildings' energy or optimizing its HVAC. So imagine your home magically knows what to do. Let's say you don't mind when you do your laundry. You just want it to be done at some point. So you put the clothes in at a given time during the day, and then your home knows based on its predictions of the weather, renewable energy availability, and also your occupant usage, it knows when to turn that machine on and sends the signals so that it reduces cost and also reduces emissions. This is a great example of AI for buildings. And here is that paper, Tackling Climate Change with Machine Learning. I believe we're going to put the link in the chat. That's a great opportunity to learn more. And I just want to give one case study of this. This is from Google DeepMind. They used AI for data center cooling. So it's a safety first AI for autonomous data center cooling and industrial control. And I want to explain how it works. So basically, every 5 minutes, the cloud-based AI pulls in a snapshot of the data center cooling systems, which it gets from thousands of physical sensors. And then they feed that information into a deep neural network, so an advanced form of AI, which then predicts the future energy efficiency and also the temperature based on certain proposed actions. After that, the AI selects actions that satisfy safety constraints and minimize future energy consumption. And then finally, those optimal actions are sent to the data center, where the local system verifies them against its own safety constraints before it implements them. And this has had incredible results. It actually led to energy savings of 30% and included all these features here you can see on the right, like automatic failover and smooth transfer. So if you're interested in getting early access to my thesis report on the net climate impact of AI, you can use this QR code, and we're also putting the link in the chat. And if you have further questions or want to connect more about this, I'd be happy to, either on LinkedIn or via this webinar. And I'm also, as I'm graduating, on the market now in terms of jobs. So if anyone is interested or knows someone who might be, would love to connect. Thanks so much.
Yeah. Hire Jen. She's great. Thank you, Jen. Thank you. And so let's now take some of those solutions and show you En-ROADS facilitators how you might engage other people to think about when you imagine these changes within a complex energy climate land system, how might it play out to affect emissions, temperature, and impacts? So I'm back here to the first scenario that we shared. This was that energy boost. And again, the slider extent, I can't say is calibrated to an estimate of the extent of AI. However, this is the direction you would move these sliders. And I'm going to just share actually that so you can see. I'm going to copy this scenario link. I'm going to drop it into chat so that you can play with some of these yourself. So look into chat and here it comes. All right. So some more that you just heard about, several possibilities, and I'm undoing that first energy impact. And now we're just going to look at some solutions. So one of them would be about having more renewable energy possible on the grid. You heard about the ability to analyze data about like predictive maintenance and that effect. So I'm going to go over here to look at the green area of renewable energy. If we encourage it, you can see it expand a little bit. See that green wedge growing a little bit? And I'm going to do it again. You can see in the bottom right, you can see renewable energy, primary energy demand growing a little bit. That cuts a little bit of coal use, a little bit of gas use, and brings temperature down a little bit over here. Other effects, you heard about energy efficiency in buildings and industry. That is going to be able to affect overall energy consumption. And this is one of the greatest possibilities and one of the most powerful climate solutions that doesn't get as much attention as it might. If we could use AI to boost energy efficiency in buildings and industry globally, and again, don't just think of the United States and the developed world. Most of this is happening outside, so it would need to diffuse to much of the developing world, global south. Notice what it might be able to do if we can boost energy efficiency. Look in the top left, total consumption of energy, energy demand would go down. We would need less fossil fuel energy to be burned. Therefore, overall temperature goes down a little bit. Similar with transportation systems, and this is not just vehicles. This would be also the design of public transportation system, optimization of those systems, of scooters, and setting up walkable communities is what is affected here with energy efficiency and transport. And similarly, we would see energy demand going down some, and we would get emissions to curve down a little bit. The big example that Jen shared, first one was about transport electrification, boosting our ability to have more EVs on the grid with some of the optimization and load shifting. A boost here, if we decarbonize, then this can have an important effect. Actually, I'm going to show the overall electric share of total transport. Here it is in the baseline. And if we were able to boost it significantly, it wouldn't grow just out in the 2040s and 2060s above 50%, but here in 2030s, a significant growth following the blue line, not the black line. We also can complement this. I noticed that Jen mentioned load shifting, and one of the key assumptions when it comes to energy storage is down here. And for you new to En-ROADS, what you're seeing over on the bottom is many of the assumptions in the model are changeable. In this case, well, that's the renewables, hold on, energy storage and demand response. So this is the role of hydrogen storage and leakage of that, but also the progress ratio, how much cheaper demand response systems get as we have more capacity, and then also the maximum potential for demand response. So these are things that could be boosted possibly by the successful application of AI. I'll boost another one with buildings and energy, buildings and industry, electrification as another possible area. Now note, how much I'm moving these sliders is not calibrated to a real assessment of AI's contribution. This is more directional. I want you to see in what direction would you move these, and therefore what might be the kind of impact to things like how much electrify everywhere we get, as you see in the top left. Okay, what are some other applications? Well, we've seen a good bit on the energy side, but these contributions, particularly of monitoring and analysis, you heard Jen mention it before, satellite data, the ability to look, take pictures of large parts of Earth, and then analyze the data is incredibly important in nature-based solutions in the world of deforestation, methane, landfills, etc. So let's look at some of that potential. Right now, in this scenario, we've done things on energy, but we really haven't touched overall methane emissions. And nor have we looked at just overall, we have a small decrease in greenhouse gas emissions, non-CO2. These are the short-lived forcers. I'm curious, you know why? This is interesting. See if anyone can figure it out. We have a lot of users here. Why is CO2, why are methane emissions already going down in this scenario where we didn't do anything about cows? I'm sorry I'm turning into Professor Guy, but someone write in chat, any advanced users who would know how we're already getting a reduction in this scenario. Why would we be using less methane or releasing less methane in a scenario where all we did was a bunch of energy actions, right? This isn't about that. So someone write in chat, less coal equals less, Jeffrey, yes, in chat. Less coal equals less methane. So what's happening is you have renewables, electrification, energy efficiency, meaning less coal being burned and less natural gas, says Sana. That's exactly it. Less coal, and we also had, as you just said, less natural gas, therefore less leakage. We didn't fix any leaks. All we did is we changed the overall scale of coal and gas being used. Therefore, overall non-CO2 emissions went down, and there's the benefit. And what you're getting is that blue area of energy production of methane in this stacked graph. And I'll maybe just slow down for a second. Energy production of methane is the blue. That just shrunk. Actually, I'll go back a few steps and we can see where it was well before. See, it was up here. And after we did all those actions to have less energy through the boosting of the energy revolution, we got all the way down here, less blue. Cows and overall manure and rice is in agriculture here in yellow, and then waste, landfills, and wastewater is in brown. Okay, we were talking about satellites and using AI to analyze satellite data. For example, where are the leaks in coal systems and in natural gas pipelines? That lives under here. So when someone asks about AI in this application, go under here, under wasted leakage, and say, we could find leaks. Watch the blue line, the blue area on the left. It shrinks as we apply 90% of potential reduction in methane leakage from energy systems. AI could help. Probably not 90%, but it could help. I'm going to boost it a lot because I want to dream a bit here. From waste, landfills, etc. We could use AI to analyze that kind of data and look at the brown area shrink. That's not the blue area, that's this brown area of waste methane. And then carbon dioxide from industrial processes is not as much of an AI kind of issue, but nitrous oxide in industry, F-gases, finding the refrigerators that are out there, the coolants that are spread out around the world right now, thrown away, slowly leaking, fluorinated gases, that would reduce overall. Do you notice that effect is in the top right? Not in methane, but in non-CO2 greenhouse gas emissions. So there seems to be potential to use some of these tools to capture some of these non-energy, in this case, overall waste and leakage, and also in agriculture. I'm going to reduce that somewhat. You see the yellow area shrinking. There's some potential with reforestation efforts, some afforestation efforts that perhaps could get some CDR. But overall, these two big areas of monitoring and analysis, satellites, drones, analyzing that data we just looked at, and then previous what Jen focused on, optimization, process control, predictive maintenance, synchronization. There could be a contribution. Will it be this full 0.7 degrees that I just simulated? Probably not. That's not at all the scale that we're imagining. But I wanted you to get a sense of where those improvements are likely to happen and in what direction we would move them and in what time scale we would see some of these results kick in. But do not take this scenario to say this would be the solution's impact from AI quite yet. Another big one I'm noticing, deforestation. This is one of the main applications in the Amazon and other areas. Taking satellite photos, analyzing where is illegal logging happening, where is it likely to happen, some of that predictive action that we can have from AI that could possibly bring us what we really need to see in deforestation, which would be a reduction in overall deforestation. And that gets us what, another 0.1, I would guess? Yeah, if we can get some of these results. Okay, many possible applications, they are speculative. We don't know of them. I hope we're not just staring so strongly at them, and I'm not moving these sliders so much because I dream of this kind of impact. We need more rigor when it comes to how much we can really move these sliders as we imagine the AI impact via solutions. But this is that second area. What I want to do is make some more changes in the model, and then we're going to look at 3 and we're going to look at 4. So what we're going to do is start to imagine what else is needed. With a scenario like this, you'll notice what have we done in this overall scenario. What we've succeeded at is boosting the clean energy revolution. And I'm going to boost it some more. What if we get some more breakthroughs in transportation energy efficiency and buildings and energy efficiency? We have renewables. We have the clean energy revolution is taking off. The challenge we face, even when we complement it with methane, nitrous oxide, F-gases, cutting deforestation, some with CDR, is that we are getting CO2 emissions from fossil fuels. And really, this is probably one of the most important graphs in En-ROADS. We're getting a transition away from fossil fuels in this scenario. It is transitioning away, and it is leading us to keep enough CO2 being emitted that its concentrations of CO2 are high enough that temperature is going above the goal. It's going all the way to 2.3. Here's global temperature. Instead of this baseline to 3.3, we don't want that. But we also don't want to pass the 2-degree goal where it follows the blue line all the way up here to 2.3. Why? Because our hearts are already being broken by what is happening in the world. This is one of about 15 different impacts you can go look at in En-ROADS. Deaths from extreme heat is going up. It's not following the black line, but it is an unacceptable rise through this century with that blue line. I'm in Asheville, North Carolina. We just got hit by Hurricane Helene. It is still fresh in my memory. And I don't want to see just a modest improvement of the population exposed to hurricanes and typhoons from the blue line to from the black line to the blue line. We should do better. Go play with En-ROADS yourself. You can go see some of the other impacts in specific places you care about. If you care about drought in the US Southwest or whatever you tend to care about, you can see in this scenario, while better, we want to do much better than the baseline. Go look at some of those results. Overall, though, the main story here is, oh, wait, that's not the greenhouse gas concentration. I want this. We are getting those fossil fuels just to bend. How do we get them to fall more steeply? It would require more direct action in that area. Top kind of possibilities would be removing subsidies. Right now, overall subsidies, $1.5 trillion. The International Monetary Fund say we subsidize fossil fuels to the tune of 1.5 trillion. I've got a way to simulate removing it. moving those subsidies. So that might be here, it's about around halfway here. If we tax coal, is the equivalent here of removing subsidies, and oil and gas. Notice what happens to emissions from fossil fuels goes down, 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 and temperature goes down some more. Carbon pricing, of course, has been discussed for a long time and is a powerful way to disincentivize the most carbon intensive industries and uses of energy. These are ways that we could tip down that fossil fuels more slowly, more quickly. $50 a ton here, 49, gets us towards 2.1. Okay, here is a scenario getting close to 2 degrees. I want to move on to number 3. Number 3 of the 4. We have seen and learned about the possibility, and well, not even the possibility, the fact that over the last 10 years, one of the primary applications of AI has been in order to get some efficiencies in fossil fuel exploration and production. The organization founded by fossil fuel companies, International Energy Agency, had a report about digital technologies, and they talked about the potential to decrease production costs 10 to 20%. And technically, recoverable oil and gas reserves could be boosted 5% globally, the greatest gains in shale gas. And the third area that's been pointed out, and these are particularly those folks enabled emissions, maybe Ava post their website, and some of these studies like the IEA study, yield possibly could go up 15%. We saw a study by Argus about the potential to extend the shale era. So back to En-ROADS. What would be the impact, and you could probably do this in your head, if we were to boost production and basically make these coal, oil, and gas cheaper? It could be, you could imagine it as moving from a disincentive on coal, oil, and gas up towards, now I'm going to, let's look more here at overall oil. In that scenario would be peaking around 2030, and here overall gas would be peaking a little later and falling. There's the bridge, more gas, and then getting rid of gas in this scenario. What if this pressure on coal was undone by some of the gains? And again, so the pressure would be to increase overall, increase towards subsidies. Didn't change anything you saw there, right? Because it's oil and gas, the two graphs. Oil would be just more pressure up, and natural gas a little bit more up, increasing temperature slightly. Now, again, I can't stand by those changes to these numbers. The other place to explore is, what if it uncovers what was previously not discovered or producible reserves of coal, oil, and gas? And we have an assumption that we'd like to revisit. If you know somebody who wants to analyze this more deeply, this is a part of the model we really want to improve, but this is the amount of fossil fuels that are remaining. And the potential of discovering more would push these numbers up. Notice a boost in oil, and over on the right, a boost in natural gas, pushing things in the up direction when it comes to emissions and also temperature. Okay, that's the third impact. How big is it? We don't know yet. When assessing the effect of AI on climate, we should understand it. The fourth one, and I learned the most about this from a conversation with you, John, the other day, which is about the overall global rebound effect from this productivity enhancing technology of AI. So what I'm going to do is I'm going to go back to the main view. If AI is successful, it boosts productivity. Productivity boosts mean GDP per capita goes up, which means overall GDP goes up. Let's go see what would happen in this scenario if GDP went up some more. And I'm going to pull up overall energy consumption. In this scenario, boy, we peaked energy demand and it's falling because of energy efficiency. And well, that's the main reason. Yeah, all of the actions we've done on energy efficiency. However, if we were to see AI boosting GDP per capita through productivity, here's what the impact would be. It would be an increase in overall economic growth. And you can see that, watch out here again, as the overall consumption of energy goes up in the long term, possibly boosting energy demand and therefore burning of coal, oil, and gas emissions up, temperature up. So that's the fourth big impact, the global economic rebound effect. Okay, can we put them all together and test them? I'm not going to, because we don't want to come up with a definitive impact of all of these areas. But just to remind you, what were the big four that we simulated? All of them in En-ROADS. And the takeaway framework for anybody who is talking about AI impact using En-ROADS. The first you saw, energy. By boosting GDP, you can see, imagine and simulate the idea that the data centers are going to use a lot more energy or a little more energy. We don't yet know, but that will overall boost coal, oil, and gas, more coal and gas. Even if we're able to use some nuclear, we're able to use some renewables to meet those loads globally. If we get this demand, would lead to more coal and gas being burned. Secondly, what Jen talked about, solutions, the possibility that it could be applied to boosting mitigation efforts in these critical areas of clean energy revolution, electrification, energy efficiency, renewables, reducing methane, nitrous oxide, cutting deforestation, boosting CDR. This possibility in the future. Third, how much is it going to make it easier to find the fossil fuels that are the source of global warming and make it cheaper to find them and dig them up and burn them? Number four, the economic rebound effect. This productivity enhancing technology boosts GDP per capita, boosts energy demand even more than its direct use from in data centers, but just overall makes the economy bigger and more energy demanding overall. Those are the big four areas that we wanted to explore. And I think I want to, boy, we've gone through most all of this. And actually, it's time for another poll. It's time for another poll. We talked about a lot here, but what are the factors that did not get mentioned? Maybe you could do it. I didn't actually include that here. Okay. Would you write in Q&A or in chat other factors that you think should be considered? What are the other factors that you think should be considered? We said energy, solutions, fossil fuels, global rebound effect. Be curious in Q&A and in other areas. And I will also prompt you, John, if you're still here, someone who did so much work behind this. Actually, are you game, John, to reflect and add anything that was on your mind? Because I'd be curious of your reactions to this. We talked, I didn't have a chance to, oh, here he comes, great. Yeah, John, anything to add from your thinking about this that I left out or to supplement?
No, I think it's been great asking a lot of terrific questions and helping people, I hope, expand the boundary of the mental models that everybody here and many others are using to try to project the impact of AI on energy use and emissions. I think in this domain, having with Jen reviewed a lot of this literature, that what we see is a great many studies with an enormous difference in what they're projecting. And the studies tend to have relatively narrow boundaries. So as was mentioned in the chat, do current estimates of AI energy use take account of the life cycle issues of how much energy and emissions come from building the chips and building the data centers, and then at their end of life, taking care of them and getting them recycled? Most studies apparently don't, but they're so poorly documented, it's really difficult to tell. Likewise, most of the projections and studies out there do not consider the direct and indirect rebound effects that you've been talking about, which are potentially extremely important. If AI helps the economy grow faster because it's a general purpose technology like steam power back in the early industrial revolution, it's going to fuel a great deal more economic growth in all areas. And right now, even with good climate policy, that means a lot more emissions between now and the end of the century. So I think the main takeaway for me from what I've learned from Jen and others is we really need models with much broader boundaries. And when we try to do that, we're going to find there aren't enough good, reliable studies, and there isn't enough good data to help us constrain what might actually happen. So it's as much about identifying what research needs to be done going forward as um, uh, as uh, as people continue to try to assess and then mitigate the energy and climate impacts of these technologies.
Great. Thank you, John. Thank you. All right. So putting a bow on the exploration of AI and then now thinking, of course, this isn't just an intellectual exercise. This is needed in the world. 2 minutes before we started, Jen mentioned her intention on this and reminded me to think of why we're here. We're here because we hope that people use this information and these tools and these studies in order to have leaders around the world be wise about their use of this amazing technology. There are conversations in Europe right now about evaluating AI and its risk and evaluating this risk to overall society. So there is potential for collective action to guide it in the best direction. The other area of impact we hope you can use this information for is using this tool to go help people have, as Professor Sturman just mentioned, a broader, more inclusive conversation on the topic. That is why En-ROADS is free and available for you to use right now in 21 languages. And we have this training course that allows you to go learn what's behind it and engage other people. So the takeaway we hope for you, besides your understanding, is a set of tools that you could use. Ava, would you post the invitation to our Mastering En-ROADS course? Be one of the people around the world who uses it in education, in policy, and those other areas. After we close, we're going to answer many of the questions you just put in Q&A. But overall, this level of leadership at this time, at a time when we're feeling the acute impacts of climate change right now, when important leaders in the world are actually rolling back the progress of the last 20 years, at a time when the tendency could be, well, let's just hole up and deal with what's coming no matter what. We invite you to step forward to hold true to the possibility that we can bend these curves, that we can use technological advances and our wisdom to address this existential threat to human civilization and this opportunity to create a more equitable, secure world. It's not going to be easy. It's going to be worth it, my friends. Go get them and stick around if you want to be here for questions.
Drew, I just want to say, like, people can probably tell, but the conclusion is kind of, from my standpoint, what we do with AI matters, and it's kind of up to us. We can't just be thinking AI is going to solve everything for us or AI is going to destroy everything for us. I really want to encourage the watchers of this to help steer AI in the right direction, to shape it and control it and corral it to be what we want it to be.
Well said, and fantastic closing words, Jen. All right. Bye-bye, everybody.